Hello, my name is Matt Murrow, and I am presenting on PyBEAM, a Bayesian approach to parameter inference for a wide class of binary evidence accumulation models. Binary evidence accumulation models assume that there are two opposing decision boundaries corresponding to the two choices in the system, where the separation between them sets the degree of caution exhibited by the decision maker. Evidence begins accumulating from some initial bias corresponding to the black dot shown here on the left, where, for example, if this were higher and closer to choice 1, the decision maker would have a bias towards choice 1. Once the stimulus is presented, evidence begins accumulating, as shown by this blue line, until it reaches one of the two decision boundaries, corresponding to this red dot here, at which point a decision is made. Writing this model as a stochastic differential equation gives the following. Where x of t is the accumulated evidence at time t, Vx of t is the drift rate, which gives the rate of evidence accumulation, and sigma x of t is the diffusion rate and sets the noise scale in your system. So what is available to deal with these types of models? Available packages at the moment include HDDM, ChartR, FastDM, DMAT, and PyDDM. And each of these provides a different useful combination of model solution type, whether it's analytic, numerical, or simulated, and parameter estimation technique, Bayesian, log likelihood, or quantile method. However, what's missing in these is a high-speed Bayesian parameter estimation tool for complex user-defined evidence accumulation models. So we introduced PyBEAM, where BEAM stands for Binary Evidence Accumulation Models, to fill this gap. PyBEAM is an easy-to-use Python package for Bayesian parameter estimation of evidence accumulation models. It works across a broad range of EAMs, which the user can define, and it allows for time-changing caution in addition to evidence and time-changing drift diffusion rates. Further, it's highly optimized for speed. On a personal 8-year-old computer, parameter estimation takes minutes to complete. So you don't need a cluster, you don't need a brand new fast computer. This works well on even older machines. So how does this work? How do we deal with the difficulty of the expanded evidence accumulation models? And there's 3 things we really want to talk about. First is changing the model from stochastic to probabilistic. Second is getting a fast, robust numerical solution. And lastly, we need to pair it with a Bayesian parameter estimation tool. So to talk about the first of these, the stochastic to probabilistic model form, we first reintroduce the stochastic form we talked about at the beginning of the presentation, where again, x of t is the accumulated evidence, b is the drift rate, and sigma is the diffusion rate, which sets the noise scale. Though this stochastic form is easy to interpret and simulate, it's challenging to deal with numerically. So what we do is we rewrite it as the Fokker-Planck equation, which puts it in terms of probabilities, but also puts it in terms of a partial differential equation, which is a much easier item to work with going forwards than the stochastic one for our purposes. This leads us into our next bit, which is the numerical solution. And we solve this PDE for the probability using the Cronk-Nicholson scheme. And we also include a time-stepping adaptation to guarantee that we're always getting a very high solution precision, which we demonstrate here on the right with this figure we have. So this figure compares the analytic log likelihood for a simulated data set to the numerical log likelihood of a simulated data set for 75 different random parameter sets, where each of these different colors corresponds to a different type of caution boundary we're using, whether it's flat, linear, or Weibull. What we should see is that if the analytic and numerical solutions are producing the same result, all of these dots will fall on the black line, and that is exactly what we are seeing here, demonstrating that PyBEAM across different model types is achieving high accuracy. The last thing we need now is the Bayesian inference tool, and we in particular use the Python package PyMC3 for this Bayesian inference. So PyMC3 is a professionally built Python package designed specifically for rapid Bayesian inference. In particular, we utilize their history-based Metropolis differential evolution algorithm. This is similar to population differential evolution, but it requires many fewer chains. So what this algorithm allows us to do is use this program on a personal computer. In fact, what I was using before, as we noted earlier, is an 8-year-old processor, and parameter estimation with this still only takes minutes to complete. So it's a very, very fast thing to do, even if you don't have a very good computer. Okay, so we talked about the framework of PyBEAM. Now we want to move on to demonstrations of its use. So to test and validate PyBEAM, we generated simulated data sets for multiple different common model types. We then used PyBEAM to recover the model parameters, and we compared the recovered model parameters to input values. So we tested PyBEAM for a number of these common models, and the first one we chose to do is the drift diffusion model itself. So what we did is we simulated 250 data points, and we used PyBEAM to recover parameters. Blue lines on the right here in these figures corresponds to the true values, the ones that were simulated, while the gray bars correspond to the PyBEAM posteriors, what we got once we applied our program to this data set. And what we see here is that we are able to achieve parameter recovery. We are getting very good parameter recovery of the initial parameters using PyBEAM, where each of these corresponds to a different parameter within the drift diffusion model, being the non-decision time, drift, boundary location, and relative bias. Also notable is that parameter recovery was very fast. It was achieved in 2 minutes, again, with this older computer we were using. If you have a newer computer, this can easily be cut by a factor of 2. So we next examine an evidence accumulation model with time-changing caution. The goal of this program, after all, is to expand the class of evidence accumulation models we can use, so we want to do more complex things than just the drift diffusion model. We in particular use the Weibull distribution, which is already popular since it can produce many different boundary shapes and is already commonly used in the literature. So we provide the function for the Weibull boundary below, and we'll briefly talk about the parameters so we can understand what is on the posteriors on the next slide. So the first parameter within this is the boundary start, represented by A. The next parameter is the collapse parameter, where 1 corresponds to no collapse in your system, which means that you just have a flat boundary. And -1 corresponds to complete collapse, where your boundary will eventually get down to 0. Anything in between -1 and 1 will correspond to the boundary finishing somewhere between 0 and its start point A. The next parameter, lambda, is referred to as the scale parameter, but for our purposes, it basically tells you about when collapse occurs. Lastly, you have k, which is referred to as the shape parameter, and this tells you how steep or shallow your boundary is. High k gives steep collapse, low k gives smoother, much shallower collapse. So as with the drift diffusion model, we simulated 250 data points, and we used PyBEAM to recover the parameters. As before, the blue lines correspond to the actual true simulated values, whereas the gray bars correspond to the PyBEAM posterior results. Now, we only include the results for the Weibull boundary, the start point, scale, shape, and collapse parameter. We're excluding the drift, non-decision, and bias posteriors because they were very easy to recover, but those we did recover well. And also, as you can see, we did in fact recover the boundary parameters well too. All of these we were able to recover using PyBEAM. Also notable is that recovery on this computer only took about 2 to 3 minutes, which is comparable to the much simpler drift diffusion model. So even though we increased the complexity of the model, we did not dramatically increase the runtime of the program. Next, we wanted to examine the recovery of the leakage parameter, and we did this using a time-changing drift. So this is necessary because leakage is a difficult parameter to recover, and we had to design a more creative experiment in order to get it back, while also being able to demonstrate a really nice feature of the program itself. So what we did is we started with a leaky drift equal to V minus L times X, where V is the drift rate, L is the leakage rate, and X is the accumulated evidence. And then at half a second, we flip the drift from a positive to a negative, maintaining the L times X parameter as is. Then at time equal to 1 second, we made the drift positive again maintaining L times X as is. Lastly, we did this for 2 different caution conditions, both fixed boundaries, one at 0.4 and one at 0.6. So we now look at the results for this. we estimated the parameters for that just described experiment, 1,500 simulated data points, 750 for each condition. Now, we had to use so many more data points for this one because the leakage parameter is just very, very difficult to resolve. Also, we again don't show the bias and non-decision times parameters since they are easy to recover. We only focus on the parameters which are challenging to get back: the drift, leakage, and 2 boundary starts that we have. But as you can see, for both of these, we're able to recover these parameters very nicely, where the blue lines, as before, correspond to the input values, and the gray bars correspond to the PyBEAM posteriors. Also, again, to note, even though we had a lot more data points and an additional condition, we didn't have that much longer a runtime. This only took about 5 minutes to accomplish. Okay, so we've talked about doing this for simulated data sets, and that's a good validation from where we're going, but we also wanted to do this with real human data. So what we did is we used PyBEAM to estimate parameters for experiment 2 from Evans 2020, a paper that was doing a coherence experiment. Now, we also did this for other experiments within Evans, which will be in the publication for this work, but we're only going to report experiment 2 for brevity here. Now, in this Evans experiment, they had a random dot kinematogram with 4 different coherence conditions: 0%, 5%, 10%, and 40%. The participants were also given a deadline of 1.3 seconds, meaning they had to have an answer by 1.3 seconds. And the authors of this paper compared the results of fitting the fixed and Weibull Cauchy models to see which of those two better describe the data set. And that is exactly what we're going to be doing with PyBEAM as well. So after we fit this, the first thing we did was compare the choice proportion values for the Weibull and flat boundaries. So what we're showing here is on the horizontal axis, the choice proportion for the actual data set versus the choice proportion for the model results, for both the Weibull on the left and flat boundary on the right. Now, we're defining choice proportion as the number of correct over the number of error plus correct responses, and we display the coherence values in the colors listed on these slides here. Lastly, we report correlation coefficients for each of these to see how close they are to actually getting the right result back. What we find is that the results from just looking at the choice proportion are fairly inconclusive. The Weibull has a slightly higher correlation coefficient of 0.97, but it's not enough to really draw a conclusion from this. So after looking at the choice proportion, we went one step further and looked at the reaction time values. So like before, we're displaying on the horizontal axis the reaction time data for the actual data set, and on the vertical axis, the average reaction time for the model. Again, doing this for both the Weibull and flat cases with the same color for the different coherences we're displaying. We also display 2 different R-squared values on this set: R-squared core, which corresponds to the correlation coefficient for correct responses, and R-squared error, which gives you the correlation coefficient for error RTs. And looking at this does give us a really good way to distinguish between these 2 models. We find that the correlation is substantially higher for the Weibull Cauchy than it is for the flat Cauchy. And this is really nice because Evans also concluded in their work that Weibull Cauchy was the most likely decision strategy. This is demonstrating that we are able to get a very similar result using a very different technique. Now, we wanted to get one more way of comparing these data sets. Unfortunately, Evans provided us a good way of doing this. So in their work, they provided a graph of the boundary shape that resulted from this experiment, which is shown on this figure on the left here. We also report on the right our figure, which gives us the boundary recovery we received from our methodology. And what we find is that both produce qualitatively similar boundary shapes. Even though their technique was very different, it was hierarchical in nature, we're getting a very, very similar result, which is a very positive thing to see. Also of note, though we don't show a figure for this here, we found that we got similar contamination proportions. So in the Evans paper, they were also fitting this model with a contamination. We ended up getting nearly the same contamination values, or at least within the range of what they are reporting, which is another validation that we are getting a similar result to them. So to summarize, in this work, we developed the Python package PyBEAM, and what it does is substantially expand which evidence accumulation models that can be studied. Further, it makes practical Bayesian estimation of complex accumulation models and does so at low computational cost and entry barrier. So Thank you for listening to my talk, and feel free to ask any questions you might have.